Okay, welcome to the second part of our video series on glycogen degradation. So to kind of highlight where we are in our metabolic map up here. So if you remember, glycogen is here, and we're breaking this glycogen down to that glucose 6-phosphate and then generally back up to the glucose, although at that point it can enter different pathways. In this video, we really want to focus in on the regulation of this glycogen breakdown, and the enzymes involved can be controlled both through covalent modification and allosteric effectors. So we're going to be looking at both of those. If we look at hormonal control of glycogen breakdown, when you are in a state of fasting, so you have low blood glucose, the pancreas will excrete glucagon, which we saw earlier. Or if you are, say, exercising, the adrenal glands will give off epinephrine. And we're going to see that these two things are chemical signals in our regulatory cascade. So we've looked at this before, right? You've seen this picture, although we've added slightly to it. And right here in that 7-TM receptor, that epinephrine or the glucagon will come in. And remember, it's going to come in here and it's going to change these conformations, which then makes a change here. And we see this break apart. You've seen this before, right? Break apart, the GDP leaves, GTP comes in. It activates that adenylate cyclase, which makes the cyclic AMP, which activates the protein kinase A, and that's where we left off before. Okay, but now, and we just said, hey, that protein kinase A, when it's activated, so the green are activated, the pink are inactivated, when it's activated, it can phosphorylate something. It's a kinase. So what we're going to see now is that it's going to phosphorylate this phosphorylase kinase. So that protein kinase A adds a phosphate group, and now we have activated phosphorylase kinase, and we'll take a look at that in a minute. And then that phosphorylase, that activated version of phosphorylase kinase, phosphorylates the enzyme that we're calling phosphorylase. Okay, that glycogen phosphorylase. But we said for short, we often just call it phosphorylase. And that activates it, makes it more active. Okay, so we're going to step through this. Let's come down here and look at that activation of that phosphorylase kinase. So just to highlight where we are, this piece here is this here. So the epinephrine or the glucagon has stimulated our whole G protein cycle, and we've gotten down to this phosphorylase kinase. Two things help activate it. One of them is calcium ion, and you'll see that right here. Okay, so calcium ion is released by muscle contractions. Sometimes hormones release it too, and it can bond to our phosphorylase kinase enzyme, and you see those areas right here. Okay, and that partially activates this. Okay, but then what we see is that protein kinase A, yep, that's not what I wanted, protein kinase A that we activated phosphorylates it, right? So we see lots of phosphates added to all these spots. Okay, and now at that point it's fully active. And it's a kinase, so by fully active we mean it can add phosphates to something else. And so it adds phosphates to our phosphorylase, our glycogen phosphorylase. So that is what we are looking at over here, these two. Okay, so those are these right here. And we can see that you can have it in what we call the B form without the phosphates, or the A form with the phosphates. All right, and we're going to take a look at both of those. Let's see. Yeah, let's go to this next slide first. This is like everything on one slide. So this is kind of what we just said, although I didn't talk about this top part. So let's look at that. So phosphorylase exists in two forms. The B form is less active, the A form is more active. If you come over here and you picture this circular area as the active site of our enzyme, and you picture these as kind of, what's the word I want? Regulatory areas. These are sections that can shift depending on the various, think of the word I want, shift depending on the various interactions that we're seeing. Okay? And so as that happens, when these things are phosphorylated, you'll see that these sections do not cover up that active site. But down here, without the phosphate groups, the way these sit, they kind of cover these. And we're going to look at a ribbon picture in just a second to look at that. But first, I just want to review everything we just talked about, because there's several steps, right? So the A form and B form differ just by that phosphorylation, which happens on a serine residue, so it gets added to a serine residue. We already said that phosphorylation is stimulated by hormones, glucagon or epinephrine. So that's up here, right on the outside of that membrane. They're bonding, they're setting off our G protein, which activates the adenylate cyclase, which activates cyclic AMP, which activates protein kinase A, which activates our phosphorylase kinase. That was this piece. And when we added all those phosphates, the protein kinase A added the phosphates, this became active. And when that became active, it phosphorylates our glycogen phosphorylase. So that this one added the phosphate groups to this one over here. Okay, and so we have the A version, more active. We have the B version, less active. All right, and it gets better, you all, because look what we have. We have not just an A version, more active, and a B version, less active. We also have an R state and a T state. Okay, and so we can have 4 different versions of this. We can be in the R state, but not phosphorylated. We can be in the R state and phosphorylated. T state, not phosphorylated. T state and phosphorylated. Okay, the phosphorylation is controlled by those hormones, the epinephrine, the glucagon. The R and T state are controlled by allosteric regulators. So something that binds to the enzyme to change the shape of it from R to T or vice versa. Okay, if we have the phosphorylated version, okay, we have version A, take a look at these arrows. We have the option to have an R form or a T form, but look, this arrow is much longer, right? That R form is favored if we have the phosphorylated version. On the other hand, if we have the B version, and we come here and take a look at our arrows, we see that the T state is favored. Just like before, the T state is going to be the less active state. R state is more active. Okay, so if I was going to pick my most active form out of these four, right, it's going to be the one that's both phosphorylated and in the R state. Okay, if I wanted to pick my least active state, I'm going to pick the one that's not phosphorylated and it's in the T state. Okay, and again, these lines here, I don't think I discussed it too well earlier, but these are like regulatory areas, okay, regulatory regions. And when you look at these, you can see when we are down here, okay, that these regulatory regions are kind of covering up some of that active site. All right, let's take a look at a ribbon drawing of this. So we have the phosphorylated version over here, the not phosphorylated. Okay, the residues, okay, those phosphoserine residues where the phosphates are bound are right in these areas. So that would exist over here too, but they wouldn't have the phosphates. The active sites or the catalytic sites are these pink areas. And it's hard to say, but if you look, this is more open than this. Notice how that pink area is kind of more covered up by all of the enzyme protein. Same down here. Okay, hence why A is the more active version, okay, that this phosphorylated A in the R state is more active because those active sites are more open. Okay, so phosphorylase regulation differs in liver and muscle cells. Right, so these are isozymes. So if you remember, isozymes have the same function, but they're slightly different enzymes that are they're perfect for the cells that they are in, right? So we have a little bit different function, or a lot different function in liver and muscle, and so we have slightly different enzymes. There's a lot of words here that are going to be repeated down below. I stuck them here just so you'd have them all in one slide to think through later. But we're going to look at those same things with a little bit added here. We're going to start with the liver. Think about the function of your liver, right? It is so important to organisms to have this kind of consistent level of glucose. And the liver is charged with keeping your blood glucose levels constant. So the liver needs to be able to easily make glucose, all right? Hence the default in the liver is that phosphorylase A, the phosphorylated more active version. And we said when we were in phosphorylase A that the R state is favored. So the default is the most active version. Okay, so it's easy for it to make glucose. Now, we still want to be able to turn that off, and so an allosteric regulator that we're going to see is glucose. Glucose is an allosteric regulator. It can bind to one of the allosteric regulatory sites, and when it does, look at what it does. When it binds, we go from the R state to the T state, so now it is less active. Okay, as it binds, it becomes less active. So high glucose makes sense. We don't need to make as much glucose. We don't need to break down that glycogen. If you have really high levels of glucose, okay, so that was the glucose. If you have really high levels of glucose, we'll get insulin. And that insulin will cause a cascade that will cause this to be dephosphorylated. So we'll move into the phosphorylase B, which is even less active, so that we can really slow things down when we need to. All right, so some highlights about the liver, phosphorylase in the liver. Key role of the liver is to maintain adequate blood levels, right? So as a result, our default will be phosphorylase A in the R state. So in essence, our liver phosphorylase is ready to generate blood glucose unless it's signaled otherwise. Our default is that it can generate blood glucose. And glucose is a negative regulator, negative effector of liver phosphorylase by shifting it to the T state. All right, let's look at muscles. So in muscles, muscles are not charged with keeping your blood glucose level, and muscles really want to save their glycogen and really only use it when it's really, really necessary. Okay, so the default in the muscle is phosphorylase B. And we know when we're in phosphorylase B, the T state's favored. So our default is the least active part in the muscle. Remember, the B form's not phosphorylated. But now we will be able to affect this two ways. We have two, or really three allosteric effectors, but a positive and then the negative allosteric effectors. So it is positively affected by AMP. So if I look right here, if AMP binds that, it's going to shift it to the R state, okay, and kind of kick it on. So when we need to make energy, we can break down that glycogen to give us the glucose so that we can work our way through glycolysis and we can, or various metabolic pathways to give us energy. So, but we got to start by breaking down that glycogen. On the other hand, if we have plenty of energy, the energy needs of the cell are met, or we can see through our metabolites that we don't need to make the glucose. Okay, we've got a high glucose 6-phosphate. Those allosteric effectors shift us back to the T, less active state. Okay, so AMP shifts us to have more R, so it'll be more active. Okay, we'll break down glycogen more. The ATP, or the glucose 6-phosphate, will shift us more towards the T state. So we'll have these two states in equilibrium, right? But we can have more of one or the other. We need to stop glycogen breakdown. We need ways to stop that, right? And so there's several mechanisms for turning off this glycogen degradation. First one, we've already seen, the inherent GTPase activity of that G protein, right? So if you remember this G protein, this GTP, this enzyme has in it, this protein has in it an enzyme that will snip off one of those phosphates and change it back to GDP, which will not activate that adenylate cyclase. So that is one way that we slow down this whole cascade and quit phosphorylating that phosphorylase. We also see that we have a phosphodiesterase, which converts this AMP. Let's change color here. Converts this AMP back to the ATP, right? Or I'm sorry, it does not convert it back. It converts the cyclic AMP into AMP, and that does not stimulate the protein kinase A. So at that point, we've cut off the rest of this. And we have something called protein phosphatase 1, which removes phosphoryl groups, right, from both the phosphorylase kinase and the glycogen phosphorylase. So this would come in here and deactivate this. That was what was activating our phosphorylase, and it'll snip the phosphates off the phosphorylase A, also sending them back to the lesser active form. Okay, this would be based on a hormone signal, so some hormone signal would set off this protein phosphatase 1. All right, so a check here. Compare the allosteric regulation of phosphorylase in the liver and muscle. Why are these regulators different? So I'd love for you to pause and think about this, or even stop the video, study your notes, come back and look at it, and then you can listen to me talk it through. But it'd be a great self-test. All right, allosteric regulation. In the liver, we had that glucose concentration. And we said when there was high glucose concentration, it converted it to the T state. So high glucose caused it to convert to the T state, and that slowed things down. In the muscle, we said high AMP would convert things to the R state. So if we don't have enough energy, it's going to convert to the R state and the more active state. If we have high ATP, or that glucose 6-phosphate, okay, it converts it to the T state. If we've got plenty of energy, we don't need to keep breaking down that glycogen. And then the why. Why is always important. Why are they different? So in muscles, we only need the glycogen when the energy needs are above and beyond our normal homeostasis rest state. But then the liver, the primary function is to keep that glucose concentration in the bloodstream constant. And so we really need it to be able to make glucose as needed when quickly as needed. All right, next we'll look at glycogen synthesis.